In this lesson, we're going to continue our look at redox chemistry, focusing on oxidations. Remember that an oxidation is an increase in the redox level. Among the oldest and most general oxidations are the chromium 6 oxidations, collectively referred to as Jones oxidations. Here you treat an oxygen functionalized molecule, something like an alcohol or a carbonyl. You treat that with a chromium 6 reagent under acidic conditions. Typically, it's things like chromium trioxide and sulfuric acid, or a dichromate salt like sodium dichromate or potassium dichromate, again in sulfuric acid. So let's take a look at a few examples. First, we've got a simple alcohol, a primary alcohol. This is ethanol, again, the booze molecule. And when you treat this with Jones reagent conditions, it actually transforms that into a carboxylic acid. So look at that transformation. The original functional group, that alcohol, that carbon, the functionalized carbon, was at the first redox level. And in the product, it's at the third redox level. So it was oxidized twice. If you look at the second example, here we have a secondary alcohol. Again, the functionalized carbon is at the first oxidation level. But in the product now, we've made a ketone. And that carbonyl carbon is at the second redox level. Looking at the third example, here we have a tertiary alcohol. Again, that carbon is in the first redox level. Treating it with a chromium 6 reagent, and you get no reaction. You basically just get the starting material back out. So in each case, we took an alcohol, treated it with the exact same reagents, and yet had three different outcomes. In the first reaction, we made a carboxylic acid. In the second reaction, we made a ketone. And in the third reaction, nothing actually happened. There is a predictable pattern here, and it has to do with the substitution, the degree of substitution on the functionalized carbon. And it's pretty straightforward. A Jones oxidation will oxidize the functionalized carbon once for each hydrogen attached to that carbon. So if you look at the first example, we have a primary alcohol. That functionalized carbon, it's in the first redox level, but it has two bonds to hydrogen on that carbon. And that means it can be oxidized twice. And that's exactly what we see. The primary alcohol went from the first redox level to the third redox level. The second example, we have a secondary alcohol. Again, it's at the first redox level, but the functionalized carbon has only one bond to hydrogen, and that means it can only be oxidized once. And that's why you end up at the second redox level in your product. In the third example, we have a tertiary alcohol. Again, that carbon, the functionalized carbon, is at the first redox level, but that functionalized carbon has no bonds to hydrogen, and that means it cannot be oxidized, and that's why nothing happens. Now, if you think your way through this, that does mean that there is one other functional group that can be oxidized with Jones conditions, and that is an aldehyde. Because an aldehyde is a functionalized carbon that has an oxygen on it and a bond to a hydrogen. So aldehydes can be oxidized up to carboxylic acids. In fact, that's how the first reaction here actually goes. The alcohol is first oxidized to the second redox level to give an aldehyde, which is then further oxidized to the carboxylic acid. Other carbonyls, like ketones, lack a hydrogen on the functionalized carbon, and so they cannot be oxidized. So here I have a ketone, treating it with Jones conditions, and there's no reaction. What we're going to look at next are some oxidations that are selective with respect to either the kinds of functional groups they react or the kinds of functional groups that they make. First up, we have the PCC oxidation. In fact, PCC, this oxidation is in fact a variation of the chromium 6 we saw before. The structure of PCC I have over here, and you can see that that chromium atom, that's a chromium atom in the sixth oxidation state. PCC is just a weaker version of the Jones conditions. So what's special about PCC oxidation is that it will always stop at the second redox level. So going back, take that same primary alcohol we started with before. That primary alcohol has two hydrogens on the functionalized carbon, which means it could be oxidized twice under Jones conditions. And that would bring it to the third redox level. However, here with PCC, it always stops at the second level, assuming that an oxidation is possible. And that means that this alcohol, this primary alcohol, will actually be oxidized to the aldehyde. If you look at the second example, we have a secondary alcohol. That carbon, the functionalized carbon, has one hydrogen attached to it, so that means it could be oxidized once, and that would actually make it go to the second redox level. And that's really no different than it would have been for the Jones oxidation, right? In other words, reacting a secondary alcohol with Jones conditions or the PCC conditions are going to give you the exact same result. It's going to make a ketone either way. So the real power of the PCC oxidation is in making aldehydes selectively from primary alcohols. Next, we have the Tollens oxidation. And this is an oxidation that is selective for oxidizing aldehydes to carboxylic acids. So here I have an aldehyde, and you treat it with a mixture of silver oxide under basic conditions and then an acidic workup, and it'll transform that into a carboxylic acid. And again, this could be done with the Jones oxidation, right? That aldehyde, it has a hydrogen on the functionalized carbon. It could be oxidized once, and that would lift it to the third redox level. What's useful about the Tollens oxidation is that it will not react any other functional groups. It only reacts with aldehydes. So if you had a complicated molecule that had lots of different functional groups on it, an aldehyde and some alcohols or whatever, the Tollens oxidation would only oxidize the aldehyde. It wouldn't touch any of those other functional groups. Now, the actual oxygen source in this reaction is the silver oxide. And when the silver oxide gives up its oxygen, it becomes silver metal. And what happens is that the glassware that you run the reaction in actually gets coated with this sort of mirroring effect of silver metal. In fact, before aluminum was used to make mirrors, this was the chemistry that was actually used to make mirrors. Mirrors were literally silvered glass. So I have a bit of a story connected to this reaction. A few years ago, I had won a teaching award on campus, and I was invited to the president's house on campus for a holiday party. Well, one of the students that was doing research with me at the time said, "Oh, you should take a gift to give to the president." So after brainstorming for a while, I thought, well, how about I make something, use my chemistry knowledge and be a total dork and give them a sort of chemistry themed, holiday themed gift. So what I did was I took a small test tube and I ran the Tollens oxidation in it. And what I did was I silvered the entire inside of that test tube to make it like almost like a silver bell, right? Holiday theme. And then I had the student tie a nice blue bow out of some ribbon that she had and kind of attached it to it to make sort of like a Christmas tree decoration. So that's my dorky Tollens oxidation story. Well, so far, all the oxidations that we've seen worked on oxygenated functional groups, things like alcohols and aldehydes. What's interesting about these last oxidations is that they are actually oxidations of alkenes. We're going to look at two reactions. First, we have epoxidation. Epoxidation is the reaction of an alkene with a peroxy acid to give an epoxide. And an epoxide is really just a special ether. It's a three atom cyclic ether. You can see the structure here. And this reagent here, this is the peroxy acid. And it kind of looks like a carboxylic acid that kind of got a little excited. It's got an extra oxygen in between the carbonyl carbon and that hydrogen. In fact, that's where the oxygen of the epoxide comes from. Now, a really commonly encountered and useful peroxy acid is a compound called MCPBA, stands for metachloroperoxybenzoic acid. Regardless, if you ever see MCPBA written somewhere, just recognize it. It's just a specific peroxy acid, a really commonly used one for making epoxides. Our last oxidation is absolutely one of my favorite reactions of all time, and that's ozonolysis. In fact, the name tells you what it is. Ozone, so it's going to involve ozone, and lysis, meaning to cleave. Here we're going to cleave an alkene in half using ozone. So here we've got an alkene, we treat it with ozone, O3, under very, very cold conditions, and then we finish the reaction off with this sulfide. This is dimethyl sulfide. And you can see that the alkene was cleaved in half right at the double bond. The way I like to look at it is if you take the alkene and you cover up half of the double bond with your thumb and replace your thumb with an oxygen and then do it again on the other side of the alkene, you've got your two products. In this case, because each carbon of the alkene had a methyl group and a hydrogen attached, we end up with two identical molecules, two aldehydes in this case. If we had started off with a more highly substituted alkene, we might end up with ketones instead of aldehydes. It's really just a matter of what groups were attached to the alkene to begin with, because they're going to remain attached in the product. Ozonolysis has to be done at really, really low temperatures, largely to avoid the reaction exploding. And I got to do a lot of these when I was in grad school. One of the cool things about the reaction is that ozone is actually colored. It's actually kind of a purplish blue color. And what happens is you generate this ozone with a special machine that basically takes oxygen, O2, and zaps it with electricity. And it creates a small stream of very dilute ozone. And then you bubble that gas into a solution that contains your alkene. And the ozone basically reacts immediately and starts making these sort of explosive compounds that you have to keep cold. Well, once you've added enough ozone so that there's no more alkene left, well, then ozone starts to build up in the solution. and you start to see that sort of bluish purple color coming out. So the reaction essentially tells you when it's done. You know that you've added enough ozone when the solution turns purple, because that means there's no more alkene for the ozone to react with, so you start building up a concentration of ozone.